Okay, good afternoon, everybody. I'm Eric Martin from the HVAC Energy Research Center. Pleased to be here to give you an overview of a few projects we have going on that fall under the theme of optimizing HVAC performance in new and existing homes. Just so we're on the same page, HVAC stands for heating, ventilating, and air conditioning systems in buildings. So all the projects in general support an overall goal of the current administration to achieve an equitable transition to a decarbonized energy system by 2050, starting with a decarbonized power sector by 2035. To do that, we really have to consider buildings which generate 1/3 of the nation's carbon emissions, use 40% of the nation's energy, and 75% of the nation's electricity. HVAC systems in homes consume 38% of a home's total energy use. The chart that you can see on the right is from an end-use monitoring project we did with Florida Power and Light and Department of Energy a few years back, and you can see how that breaks down in homes in Central Florida. So optimizing HVAC energy use is important because of the number of systems that are installed each year. This includes the systems installed in about 1.7 million new homes each year and systems replaced in about 5 million homes each year. So these projects that I'm going to talk about are funded by two Department of Energy initiatives. The Building America program is something we've been a part of since the late 90s. And that program looks to develop innovations for residential building energy performance in the context of durability, quality, affordability, and comfort. And then the second program is a new initiative from Department of Energy called the Advanced Building Construction Initiative that looks to integrate those innovations into state-of-the-art construction methods to accelerate adoption. So the first project deals with ventilation, and it's important because we build homes, new homes now tighter than ever for energy efficiency reasons, which means that we need to mechanically ventilate these homes to maintain good indoor air quality. That ventilation air that we bring in for dilution purposes has energy and comfort implications, so it's important to optimize these ventilation systems. This project is a collaborative effort between HVAC and a couple of different national labs in University of Illinois. Each team is recruiting about 30 homes in a couple of different climate zones. We have climate zones 2A and 3A. We've recruited and collected data in 50 homes so far. And what we're looking to do is measure contaminants of concern in these homes and also characterize the type and operation of the mechanical ventilation systems in the homes, so that we can evaluate the effectiveness of those ventilation systems at controlling contaminant levels. This project is kind of wrapping up. It's been going on for a long time. It was delayed because of the pandemic. We're hoping that the results are going to inform various stakeholders about proper design, installation, and operation of the systems. The instrumentation we acquired as part of this project helped us do some research in response to the pandemic, looking at how to create isolation spaces in homes to minimize transmission of infectious diseases. And this project also spawned some previous collaboration between HVAC and the College of Community Innovation and Education, who was working on some outdoor air quality projects. And so we teamed up and wrote some proposals about air quality and energy equity. This is a busy slide, but I just wanted to show what the instrumentation, some of the instrumentation looks like when installed in the homes. Our focus here is on particulate matter, specifically PM 2.5. We're also looking at NOx, formaldehyde, radon, and carbon dioxide. The next project is looking to inform industry about the implications of improper HVAC design and installation. And some studies have found that that can result in 30% extra energy use just by not designing and installing the systems properly. So we've teamed up with Proctor Engineering Group, which is based out of California, and they're leading a field study that's looking to identify the prevalence and severity of design and installation faults in a sample of 85 homes, about half in the Southwest US and about half in the Southeast US. The faults that we're looking at include improper sizing, refrigerant charge, airflow, and duct leakage. We're working with various utility partners to help us recruit these homes, and they're inviting customers to participate that had a newly installed system within the past 12 months. And we have field teams that go out and characterize the quality of that installation. HVAC's primary role is to quantify the energy impacts of select faults by collecting data in some of our laboratory homes. We're using our side-by-side lab home facility you see in the photo there. One of the buildings configured to be a quality install, and then we impose faults in the system of the other building, and we compare the energy use between the two. So the lab data collection is nearly complete. The field data collection portion of the work is really just beginning. It was also delayed because of the pandemic. We're hoping the results are going to inform stakeholders that are looking at how to consider installation quality when estimating building energy performance. And the intended outcomes, of course, are to hope increase the use of best management practices when installing HVAC systems. This slide just shows some additional detail of our side-by-side laboratory facilities that we're using. That was designed as a 3-bedroom, 2-bathroom home, but the interior floor plan was never really built out. So inside the labs, it's really one big open space, and we have some what we call interior wall modules to simulate heat and moisture capacitance that you'd find in a fully built out home. This last project is funded by the Advanced Building Construction Initiative, and DOE put out a challenge for teams to come up with retrofit strategies that could achieve deep energy retrofit levels of energy efficiency. So 75% reduction heating, cooling, water heating use. But they also challenged us to come up with an innovative way to apply the retrofit to a large number of buildings and deploy it quickly with minimal disruption. So what we are working on is primarily mechanical system retrofit that involves providing a high efficiency mini split heat pump and heat pump water heater. And we envision bundling this in a pre-packaged mechanical system pod that's largely assembled off-site, can be delivered to the home and installed relatively easy and relatively quickly. The other innovation we have is we've devised an approach to power these components with a very modest photovoltaic system that provides some of the power, and then the electrical grid backs up the whole system, providing power when there isn't enough PV available. We've configured this so that no excess PV energy is sent to the grid, which minimizes lots of complications. So we just wrapped up our phase 1 documenting performance of our pilot systems, and we submitted a proposal for phase 2 that, if funded, is going to give us the ability to demonstrate pre-production prototypes in a number of homes around the country and really work with some industry partners to look at commercialization of a system. So we'd be working with both REAM and NASIO on that to look at a commercialized system and how we deploy that at scale. This slide just shows some photos of additional labs that we have at FSEC where we tested the pilot systems. The Building Science Lab was designed to mimic a typical Florida small commercial building. And then we have a manufactured housing lab on campus as well that is a fully furnished residential lab home that operates with simulated occupancy. So wrapping up here, my last slide, just wanted to talk about some near-term opportunities with these projects. So in terms of ventilation, I think we're going to see more sensors and controls that enable smart ventilation, that enable ventilation systems to modulate in response to various factors to optimize their operation, rather than operating on a continuous basis, which is what we see commonplace today. I think we'll also see some active air cleaning technologies that'll come into play and be combined with the dilution mechanical ventilation that we're primarily using now. And then I think we'll start to see building design and retrofit strategies that will help the building be configured to minimize transmission of infectious disease indoors. In terms of HVAC quality, installation, and operation, there's a push to standardize inclusion of onboard fault detection and diagnostic systems across the board in all new systems that are going to help minimize faults that occur either during installation or over the life of the system and help with the operation and maintenance of the system. As we push towards electrification of heating fuel so that we can power more of that with renewable energy, along that path, what we're starting to see now are lots of dual fuel systems that are kind of being used in the interim before we get to full electrification. And there's some push to develop some integrated controls to coordinate operation of those dual fuel systems. And then we're also seeing a big push to connect buildings to the grid to provide a number of different services. And that affects the operation of HVAC systems as well. Lastly, the PVGEMS retrofit strategy, as I mentioned, our phase 2, DOE is really pushing towards demonstration and commercialization. So we think there's some opportunities here to really develop something that would be put in use on a large scale. So we're looking at tech transfer, commercialization partnerships industrial design, engineering, and manufacturing partnerships, and also potential partnerships dealing with controls and power electronics. Lastly, I think looking out into the future, it's important that we consider the fact that the buildings we're designing today are going to be around for a while. So we need to think about how those are going to respond in the context of a changing climate. And I just include an excerpt here from a recent paper co-authored by my colleague Danny Parker, and he worked with a number of colleagues in Europe to look at the impact of changing climate on European buildings. And what they're finding is that the currently available weather data sets that we use to design buildings cannot assure reliable results with building simulations, and that the energy balance, at least in European buildings, is going to significantly change in the future. And so what we see is a decrease in heating with a corresponding increase in cooling. And so we have to be able to design buildings that are capable of adapting to that changing climate. With that, thank you. I do include a link here to a video we have on our PV Gems project. It's about a 10-minute video that provides a much more detailed overview of what that system is and what it's capable of.